In this part, we will talk about different hybrid reaction separation processes. So far, we have considered reaction and separation carried out in a sequence of separate units. If both reaction and separations are carried out in the single unit, the conditions in the reactor or in the unit need to be suitable for both reaction and separation. And an important example where hybrid reaction separation processes can be beneficial is in the case of reversible reactions. Let's consider here a reaction A plus B forms C plus D. As you know, we want to enhance the forward reaction to get good conversion of A and B. And as you know, if we can remove the products, we could increase the conversion. And here we are considering Le Chatelier's principle. So the question is how we can remove C and D while also allowing the reaction to continue. And another question is that how can we allow the reaction to progress while the separation is happening? In particular, what are the conditions that would allow both reaction and separation to take place simultaneously? Oftentimes, the reaction temperature is quite a lot higher than the separation temperature, which makes simultaneous reaction and separation difficult or impossible. So let's look at an example where a reaction and some separation takes place simultaneously. So in this example, we have A plus B reacting to form product C and D. The reaction is exothermic. It means that it releases energy. The heat of reaction is negative because the enthalpy of the product is less than the enthalpy of the reagents. So one option to separate C from D is that we can actually vaporize C if it is, let's say, more volatile than the any other component. So by vaporizing C, it can leave the reactor system, and then the reagents A and B will react further to try to increase the presence of C again. Okay, so by removing C, we have shifted the reaction forward. And if C is volatile, obviously that is good because we can remove it, but we still need heat to vaporize C. And one good idea is that we can use the heat of reaction or the exothermic reaction, and then we can use that to vaporize C. But a problem can be that if we are vaporizing C, the heat might also vaporize A and B as well. It means that we have now no reactants left into the system to move this reaction forward. But one option can be that, let's say, if we manage to vaporize C with A and B, so we can actually use the vapor stream and condense it and return this reactant back to the reaction and maybe some of the C as well, and that will keep the reaction going in the forward direction. So we can keep on removing C from the system and keep on refluxing A and B to the reactor to keep the reaction going. So C is more volatile than A, B, and D. Sorry, we allow C to be removed from the top of the reactor, and we continue the reaction. But if D is the heaviest product, then we can also take out D, A and B with D, and because D is the heaviest product, it means that A and B are more volatile than D, so we can actually vaporize A and B in the reboiler and then again recycle them back to the reactor, and by doing that we can actually keep the reaction going. But let's think about how we could engineer this process. So we want to do some condensing of A and B and some reboiling of A and B. We want to separate A and B from the A, B, and C overheads, and we want to separate A and B from A, B, D mixture, leaving the bottom of the reactor. We could do those separations using some separation stages, but this is starting to sound like distillation column again. We need some reaction to take place inside the distillation column. If we can find some way of making the reaction happen, this can be engineered. we may need a catalyst to be present to enable the reaction to proceed. So we need to find a way of having fluid catalyst contact inside the column, while also enabling countercurrent flow vapor and liquid in that reactive zone. Okay, so by looking at these options, we can actually form a reactive zone inside a distillation column. The reaction could be taking place in a homogeneous environment. In other words, only fluids are present. We would need some way of enhancing contact between the liquid and the vapor in the column to allow C to move upwards in the vapor phase uh, through that section towards the condenser, and to allow D to flow downwards through the reaction zone towards the reboiler. Okay, and the diagrams here show three different ways of doing this. One is to simply have a liquid on a standard distillation tray with vapor bubbling through the liquid layer that mostly used in standard distillation columns. Another is to use packing, and this packing can be either random or structured packing. These packings allow the liquid to form thin films, and these thin films packing can have excellent contact with the vapor phase. Okay. The most important thing is that the design of the packing should be such that it allow enough residence time for the reaction to take place. Now, if we have a solid catalyst present in the system, then we want to make sure that the catalyst stays in the column, especially in the reactive zone, to allow the reaction to take place. Again, we need or we want to actually enhance the contact between the liquid and vapor to allow sufficient residence time for the reactants to react. And there are different ways to do that. And for example, one of the option is here you can see on the top left corner, that is called a tea bag configuration. So here what we do is that we have a mesh, a very fine mesh that holds the catalyst, and so you have these different pallets of this catalyst throughout the reactive zone, and the liquid and vapor can pass easily through this mesh, but the mesh is fine enough so that it doesn't allow the catalyst particles to escape. Then you have another option that is what we call a sandwich configuration, and here you have catalyst that is supported in between this structured packing. Okay, and again the idea is that to enhance the liquid contact with the vapor, and that's where the packing is very effective. And because the catalyst is supported in between this packing, so the reaction also happens there. Third, we have an option called monolithic structures, and these monolithic structures are a very effective way of containing the catalyst in the reaction, and actually this structure itself is the catalyst, and it allows the space and the surface area required for the reaction. Okay, so again you can see that it has these holes where the liquid and vapor can get in contact in the presence of the catalyst, that is the packing itself. Similarly, we have a porous solid such as a ceramic foam or a solid sponge, as you can see here, and that porous solid allows liquid and vapor to contact each other. It is also coated with the catalyst so that the liquid comes in contact in the presence of the catalyst. Let's have a look at an example of reactive distillation, and here we are looking at selective hydrogenation of benzene. And the context for this study is hydrogenation in petroleum refining. So benzene is very well known carcinogen. For health reasons, its concentration in gasoline has been limited by legislation in recent years. So the problem here is that how can we selectively convert benzene to non-carcinogenic cyclohexane or cycloalkane products? Okay, so benzene is a part of a complex oil mixture with lighter and heavier components present in the same stream. The reaction needs to be selective to the benzene and not destroy other valuable components in the oil mixture, because these components have a positive impact on the octane number of the gasoline product, or octane number is a quality of the gasoline product. Okay, so we want to have a higher octane number. Here we focus on three close boiling components: benzene, toluene, and xylene. And we want to explore reactive distillation process where we want to actually selectively hydrogenate benzene to the point that the concentration of the benzene is less than 1%. The hydrogenation of toluene and xylenes should be avoided. So again, the goal is that we want to do the reaction and separation within the same distillation column. Before we go and look at the process, please take a few moments to review the boiling point data on the slide so that you can understand the discussion in the next slide better. So here you can see the reactive distillation process, and this process was developed to allow the selective hydrogenation of benzene. On the flow sheet on the right, you can see that the hydrocarbon and hydrogen are fed to the distillation column with the trays towards the bottom of the column. And then you have a reboiler here that is actually vaporizing the feed, and then that vapor is traveling upwards. On the upper end, you have the cooling or the condenser, where actually you are condensing some of the vapor products, and then you are using it to come back to the column in the countercurrent way as a reflux. Here in this box here, where the axis, that is the reactive section where the catalyst is, and the countercurrent flow of the vapor and the reflux allows the benzene and toluene and xylene to be selectively reacted over this catalyst. Some light material is removed in the vapor phase, having not been condensed in the condenser. So unreacted hydrogen is recycled back to the reactor. Although it is not shown here, but you might need a compressor here in case if the pressure of this stream is not equivalent to the pressure in the column. And as it seems that it's at 6 atm, so it's very much possible that you need a compressor here. So the references at the bottom of this page state the benefits of this technology, and the benefits include selective nature of hydrogenation, and also the use of milder conditions than the conventional hydrogen technology. And the milder conditions would tend to employ less preheating and lower pressure, so cheaper overall operation. So this reactive distillation technology provides us several advantages in terms of lowering the operating and the capital costs of the process, but it adds additional challenges in terms of the complexity of the process. Also, because this is an exothermic reaction, so we need a good temperature control on this system, because we don't want a thermal runaway in these kind of processes. So let's have a look at another example of a hybrid separation process where a reaction is combined with a membrane separation, okay, in contrast to a distillation unit. So this is just to give you an example that we can combine reactions with different separation technologies, not only with distillation, to achieve a hybrid nature of separation and reaction. So the type of membrane that we are using here, or the type of method of membrane separation that we are using here, is called pervaporation. So pervaporation is a membrane separation process in which the upstream of the membrane is in contact with a feed liquid, while a vacuum is applied on the downstream of the membrane, and the liquid permeate, the liquid that travels through the membrane vaporizes somewhere between the upstream and the downside of the membrane. And at the downstream we get the vapor, and then you can use some kind of cooling system like a condenser or a cooling water system to condense that vapor that is received at the downstream of the membrane. So in this case, we have another reversible reaction where an alcohol and an acid react to form an ester and water. Again, the reversibility of the reaction encourages us to remove at least one of the products to enhance the conversion of the reagent. So here you can see in this diagram that this is the reaction stage, okay, where the acid and the alcohol react, and then the product of this reaction, we normally fed it to the pervaporation system, where we extract some water from the system, and then the remaining alcohol and acid, they are recycled back to the second stage of the reaction. So from each stage, by using this membrane, we are extracting some amount of water, and as such, we kind of push this reaction forward by removing one of the product, that is the water here. So as you might have noticed that most of these hybrid separations, we are using them for reversible reactions, but that is not only the case. We can also use them in non-reversible reactions, but again, because of their complex nature, we try to normally avoid them, because to make them work, all the conditions need to be right. And so we only use them when capital cost of the other process is very high. Let's close this chapter with an overview and summary. We looked at different separation technologies and the selection process. I recall that the technology selection is based on exploiting differences in physical properties. We also noted that the separations don't take place spontaneously, and most often they incur considerable costs. We focused mainly on distillation because it is very widely used, and we reviewed some of the key decisions in terms of the design of distillation column and its sequences. We had a brief introduction to hybrid reaction processes, emphasizing the elegance of some of the solutions that can both overcome equilibrium limitations and enhance conversion of expensive raw materials. Finally, we acknowledge that the separation costs and energy consumptions can be very significant, but a good design of separation process ensure good technical and economic process of the process flow sheet. And this is one of the key challenges of process synthesis design. Here we summarize the key learning outcomes for this lecture. Some of these will be further explored and expanded in the synchronous sessions. And with that, I want to thank you for your time and see you in the synchronous lecture.